Sorry about that. I accidentally killed the stream. But I guess it's a good bookmark for this chapter. We're just starting this chapter. So let's go into chapter 14. Make sure we got everything we need in here. Looks good. So let me just make sure that's correct. Yep. Cool. So let's start reading this. And I'm going to go for another 30 minutes, and then I'm going to break for lunch. So in chapters 4, 5, and 13, we looked at file I/O with a particular focus on regular disk files. And in the following chapters, we go into detail on a range of file-related topics. This chapter looks at file systems. Chapter 15 describes various attributes associated with a file, including the timestamps, ownership, and permissions. Chapter 16 and 17 consider two new features of Linux 2.6, extended attributes and access control lists. Extended attributes are a method of associating arbitrary metadata with a file. That's cool. ACLs are an extension of the traditional Unix file permission model. Chapter 18 looks at directories and links. Okay. The majority of this chapter is concerned with file systems, which are organized collections of files and directories. We explain a range of file system concepts, sometimes using the traditional Linux ext2 file system as a specific example. I wonder what is the file system ext that I'm on? What version? Let's do mount grep ext. Pretty sure. Am I running BTRFS? BTR. Yeah, I'm running BTRFS for everything. Linux ext versions. So he's talking about ext2. Yeah, so I think we're on 4, right? ext4 introduced in 2006. This stuff hasn't been iterated on a lot. Introduced 2001. Introduced 1993. History, maybe? This should be included in this book. Okay. Where do we leave off here? Oops. Alright. We also briefly describe some of the journaling file systems available on Linux. We conclude with the chapter with a discussion of the system calls used to mount and unmount a file system, and the library functions used to obtain information about mounted file systems. Device-specific files, devices. This chapter frequently mentions disk devices. So we start with a brief overview of the concepts of a device file. So there's like character devices and there's block devices. And character devices are things like terminals. They're more streaming. Whereas block devices are more like kind of like normal files where you're seeking to a specific location in the specific block in the file and doing I/O on those blocks. I don't think you can seek on a character device. I think that's the main difference. But yeah, let's continue reading. A device special file corresponds to a device on the system. Within the kernel, each device type has a corresponding device driver, which handles all I/O requests for the device. A device driver is a unit of kernel code that implements a set of operations that normally correspond to input and output actions on an associated piece of hardware. The API provided by device drivers is fixed. And includes operations corresponding to systems calls open, close, read, write, mmap, and ioctl. The fact that we haven't really talked about ioctl in this book yet. I'm surprised we've gotten this far and we haven't really had a lengthy discussion on it. The fact that each device driver provides a consistent interface, hiding the differences in operations of individual devices, allows for universality of I/O. Some devices are real, such as mice, disks, and tape drives. Others are virtual, meaning there's no corresponding hardware. Rather, the kernel provides via a device driver an abstract device with an API that is the same as a real device. Devices can be divided into two types. Character device handle data on a character-by-character basis. Terminals and keyboards are examples of character devices. Block devices handle data a block at a time. The size of a block depends on the type of device, but it is typically some multiple of 512 bytes. Disks are a common example of block devices. Device files appear within file systems. Device files appear within file systems just like other files, usually under the dev directory. The super user can create a device file using the make nod command. I've never used that. Man mk nod. I never heard of this. Make block or character special files. Why is it nod? Let's ask AI. Why is command used to create devices called mknod? Make node. Device files or nodes. The word node in Unix terminology refers to inode, index node, or a special file node. A device file is a kind of inode that connects the file system to a device driver. I didn't know that. Make a file system node where the node can be a block device, character device, or a FIFO pipe. Alright. Create the special file name of the given type. Mandatory arguments to long operation options. Okay. To say make node, the name, the type, give me a common example of using mknod. So you say, hey, I'm going to make node. Can you make device files under directory other than dev? So I can do one of these. I can say, hey, make nod. I want it to be under test.dev, character device. Null device, a 1.3. 1.3. Sudo bang bang. Yeah, it's at their root. Cat test.dev. If I echo foo into test.dev, change owner to C0 test.dev sudo cat test.dev. Yeah. RM test.dev. Okay. So you need the sudo permission to make the device, but once it's made, you can then take ownership of, root has to give you ownership of it, but once you have ownership, you can delete it if you want. That's pretty cool. All right, back to chapter 14. Oh, I did want to do mknod. Let me just do test2dev. And then change own again. And then I wanted to say get status. It doesn't even recognize it. It's like, hey, that's a character device. I think that's what the C means, is character device. Yeah, that's what we gave it up here. So rm test2. All right, chapter 14. Cool. All right, let's kill this. Okay. Let's continue on. Okay. Using the make node command, and the same task can be performed on a privileged. Wait a minute. Let's start over again. Device files appear within the file system, just like other files, usually under the dev directory. Yeah. Super user can create a device file using the make node command, and the same task can be performed in a privileged cap make node program using the make node system call. We don't describe the make node make file system inode. Okay. System call in detail, since it uses its use is straightforward, and the only purpose for which it is required nowadays is to create device files, which is not a common application requirement. We can also use make node to create FIFOs, but the make FIFO function is preferred for this task. Historically, some Unix implementations also use make node for creating directories, but this use has now been replaced by the make dir system call. Nevertheless, some Unix implementations, but not Linux, preserve this capability in make node for backwards compatibility. See make node manual page for further details. In early versions of Linux, /dev contained entries for all possible devices on the system, even if such devices weren't actually connected to the system. This meant that dev could contain literally thousands of unused entries, showing the task of programs that need to scan the contents. Slowing the task of programs that need to scan the contents of that directory, and making it impossible to use the contents of the directory as a means of discovering what devices were actually present on the system. In Linux 2.6, these problems are solved by the udev program. The udev program relies on sysfs file system, which exports information about devices and other kernel objects into user space via a pseudo file system mounted under sys. Boop. Hartman provides an overview of udev and outlines the reasons it is considered superior to devfs. Is /dev devfs mount grep for /dev. Does that thing use devfs? Dev tempfs. Udev? Is there udev here? No. Sys udev? Sysdev. Block. Cool. Char. Ooh, a lot more char. Alright. Device IDs. Each device has a major ID number and a minor ID number. The major identifies the general class of device and is used by the kernel to look up the appropriate driver for this type of device. The minor ID uniquely identifies a particular device within a general class. The major minor IDs of a device file are displayed by the ls-l command. The major and minor IDs are recorded in the inode for the device file. We describe inodes in section 14.4. Each device driver registers its association with a specific major device ID, and its association provides the connection between the device special file and the device driver. The name of the device file has no relevance when the kernel looks for the device driver. On Linux 2.4 and earlier, the total number of devices on the system is limited by the fact that device major and minor IDs are represented using just 8 bits. The fact that major device IDs are fixed and centrally assigned by the Linux assigned names and numbers authority. I didn't know this. I didn't know about this. It's kind of like IANA, but for Linux. That's funny. LANANA.org. Linux assigned names and numbers authority. It's like a banana. It's a lanana. That's funny. Links device list. Oh. What happened to their website? Is this thing still operational? That's a bummer. Seems like it moved to Linux Foundation. How old is this thing? I guess it was updated in 2018. They need to fix their 404s though. Alright. Let's go back to the text. Further exacerbates the limitation. Linux 2.6 eases the limitation by using more bits to hold the major and minor device IDs, respectively 12 and 20 bits. Disks and partitions. Regular files and directories typically reside on hard disk devices. Files and directories may also exist on other devices such as CD-ROMs, flash memory cards, and virtual disks. But for the present discussion, we are interested primarily in hard disk devices. In the following section, we look at how hard disks are organized and divided into partition disk drives. A hard disk drive is a mechanical device consisting of one or more platters that rotate at high speed or the order of thousands of revolutions per minute, magnetically encoded information on the disk surface is retrieved by modified by read-write heads that move radially across the disk. Physically, information on the disk surface is located on a set of concentric circles called tracks. Tracks themselves are divided into a number of sectors, each of which consists of a series of physical blocks. Physical blocks are typically 512 bytes, or some multiple thereof, in size, and represent the smallest unit of information that a drive can read or write. Although modern disks are fast, reading and writing information on the disk still takes significant time. The disk head must first move to appropriate track, seek time, and then the drive must wait until the appropriate sector rotates under the head, rotational latency, and finally the required block must be transferred, transfer time. The total time required to carry out such operations is typically of the order of milliseconds. By comparison, modern CPUs are capable of executing millions of instructions in this time. Disk partitions. Each disk is divided into one or more non-overlapping partitions. Each partition is treated by the kernel as a separate device residing under the dev directory. The system administrator determines the number, type, and size of partitions on a disk using fdisk command. The command fdisk-l lists all partitions on a disk. Linux-specific proc partitions file lists the major and minor device numbers, size, and the name of each disk partition on the system. Let's list that. Proc partitions. Cat it. What is DM0? So I think this is used for booting, maybe? It's a smaller partition. Let's ask. I need to do it more like this, yeah. So that's AI. What is DM0 and ZRAM0? Oh. Yeah, EFI or boot. Device mapper. Virtual block device by the device mapper. Oh, so this is the encrypted volume. So this is probably like everything on this partition is encrypted, and then this allows it to be decrypted, maybe? I don't know. Compressed RAM block device. Huh, interesting. Alright. This partition may hold any type of information, but usually contains one of the following. File system holding regular files and directories as described so-and-so. A data area access as a raw mode device. A swap area used by the kernel for memory management. A swap area is created using make swap command. A privileged process can use the swap on system call to notify the kernel that this partition is to be used as a swap area. Swap off system call performs the converse function, telling the kernel to cease using the disk partition as a swap area. These system calls are not standardized in SUSE 3, but they exist on many Unix implementations. See the swap on 2, swap on 8 manual pages for additional information. The Linux specific proc swaps file. Do I have any swaps here? Cat proc. Oops. Cat proc swaps. just the ZRAM 0 thing. Can be used to display information about the currently enabled swap areas on the system. This information includes size of each swap area and the amount of the area that's in use. What is the size? It is 4 megs? That seems like a memory. Why would... I don't know. Okay. We are at Filesystems 4.3. We go into inodes. 4.4, the virtual file system 14.5, journal file systems, single directory hierarchy and mount points, mounting and unmounting file systems, advanced mount features, a virtual memory file system, obtaining information about the file system, and summary. So we got quite a lot ahead of us on file systems. I'm gonna wrap here and get some lunch, but I will be on in a little over an hour from now to resume reading about file systems. Cool. Catch you then. Bye.